So in this video we're going to introduce something called a Maxwell Boltzmann distribution. Now Maxwell Boltzmann, they're the name of two scientists. Distributions are graphs, curves that show how things are distributed. So how maybe marks on a test are distributed. So we could have a think about what that might mean or how we would put together a distribution. What we're looking at here is a distribution curve, and this is actually shown as lots of bar charts. So this is a distribution curve for the results of the UK Chemistry Olympiad. Now the Chemistry Olympiad is a very difficult extension paper that students who've got an interest in chemistry can take in their second year. It's a challenging paper that's set beyond the level of A level and challenges your problem solving skills. And what you can see is that here actually somebody did score 0 marks, and in our distribution we're going to look at nobody's going to get 0, but very few people score absolutely nothing. But then we've got quite a lot of students scoring quite low marks and very few scoring the very highest marks. So if we were to draw a line over the top of our curve, this would be a distribution, let's get that a bit tidier, a distribution curve. Okay, so we're showing the general shape of the distribution. So it's like going around with a tally chart and going and asking people something and then showing how that is spread out. And that's what we mean by a distribution curve. So our distribution curve that we're looking at is a distribution of the energies of particles. So if we're looking at the energies, we'll put the energies along the bottom, just like we would have put the score in the test along the bottom. And at the side, we're not measuring the number of people with that energy, we're measuring the number of particles, but it's a distribution, so it's a number of something up the side, it's a number of particles. Now there are some key features to this curve, so before we attempt to draw the shape, we're going to talk about the key features. So we get these into our sketch graph and we're going to hit the marking points that the exam board want. So feature number 1, there are no particles with 0 energy. So what's that going to mean for our curve? That's going to mean our curve is going to start at the origin. So our curve is going to start exactly on the origin. 0 particles have 0 energy. There is no maximum energy that a particle could have. So what that means is our curve is never going to touch back down onto the x-axis. It's going to become, the fancy word for this is asymptotic, so it's going to follow along in a parallel line to the x-axis. So there's going to be no maximum energy, so we don't want the graph to rejoin the x-axis, and the exam board will look for that. It has to start at the origin, but then never touch the x-axis again after that point. The modal energy, the most frequently occurring energy, so the one that most particles have, is fairly low. So our peak is going to be to the left. So have a back look at our graph of that exam. That is something where the most frequently occurring score was actually 12. Okay, you might think, wow, 12 out of 86, and maybe it was out of 90. That's a very low score, but that is it. It's very low, so the peak is going to occur to the left. It's not going to be, those of you that might be studying maths, a normal distribution where the peak is in the middle. The peak is going to be to the left. That's called the modal energy, the most frequently occurring. Now the average energy, the mean, is actually going to be a bit further to the right than the modal energy because there is a lot more results still to happen, and so we need to bear that in mind. So we might want to put a little note. The mean energy is to the right of the modal energy. So the mean or the regular average that you're used to dealing with. So the mean energy is slightly higher than the mode. Now we can't know exactly where the mean energy is, but we can know where the modal energy is. It's the highest point. The activation energy is going to be much higher than all of those. So the activation energy is going to be far to the right, higher than both the mode and the median. So we're going to have that to the right. That highest curve, the highest point is going to be called the modal energy, or the most probable energy. That's the highest point. Now our next thing is that the area under this curve is going to represent the total number of particles. So again, let's look back at our test marks. The total number of students who took the test is the sum of all those bar charts. So the total number of particles in the sample is the area under the curve. So that's more of a feature that you might get asked about than is a way that we're going to draw this curve. The area under the curve is the total number of particles. And I'm going to leave the last bullet point for now because that's going to be something that we're going to add on in a minute. So we need to remember what we said. We're going to start at the origin, no particles with zero energy. That our peak is going to be to the left because the modal energy is quite a low energy. So it's going to go up quickly and then come down much less steeply, so a much slower rate of coming down. So it's going to go up quickly and then it's going to slowly come down. It's going to look very similar to that test distribution we just had. It's going to go up quickly and down much more steadily. Our activation energy is to the right of both our modal energy, which will be here, our most probable, or the modal energy. And our average energy, our mean, is probably going to be somewhere to the right of that. I'm going to write it in here. You don't have to get that perfect. The modal does need to be the peak, but the mean must be to the right of the peak, but to the left of the activation energy. And our last bullet point that we missed out is we're going to shade the area of the curve to the right of the activation energy line. And that area there, that is the number of particles that have got enough energy to react. So the shaded area is going to represent the particles with sufficient energy to have successful collisions. So with energy greater than or equal to the activation energy, so those that collide successfully. Okay, so that's just something to bear in mind. Now if we are taking this distribution curve, our next videos are going to be looking at how we can increase that shaded area, because it's that shaded area that is the key feature of this graph. That shaded area is all the particles that can react. So let's have a look back at our test graph. Here we are. So maybe right down here we've got this boundary for getting a gold certificate. It's a bit like our shaded area. Now we would all love to score gold. How can we make more students score gold? Well, there's two ways we can do that. We can lower the grade boundary. So you had to score 37 or 38 to get a gold. What if we made it so you only had to score 30? Then more people would score gold. And to achieve that, that's how you achieve that, would be to add a catalyst to provide a new route with a lower activation energy. So if we shift the barrier back, more particles will react. The other way is we could have just made the test easier to start off with, and then everybody would get a higher score, and so the whole curve would shift like this, because the people that were getting 2 might now get 4, and the people getting 4 might get the next scores on some of these, and so gradually the whole curve shifts. You might look at that and think, well, it's gone lower. Well, it has gone lower because the bit over here is higher, so the bit on the right is higher, so the bit on the left would have to be lower. But now you can see many more particles, people are getting a gold. And so these factors that affect rate in this way are temperature and catalyst, and we're going to have a look at each of those in some separate videos. We're going to look at how we plot those on our distribution curve.